Alright, let's go. Number 10. Boomerang aerodynamics. A 23,000-year-old mammoth tusk boomerang, recovered from a cave in southern Poland, was replicated and aerodynamically tested, and its flight characteristics matched designs that wouldn't reappear for another 20 millennia. The replica left the thrower's hand at 42 meters per second, climbed on a stable arc, and returned to within 3 meters of the launch point. When the researchers ran the data, the lift-to-drag ratio matched the performance envelope of modern returning boomerangs used by Australian Aboriginal communities separated from this Polish cave by 23,000 years and roughly 14,000 kilometers of land and ocean. The match was not approximate, it was precise. The original artifact was pulled from the sediment of a Blaswa cave in 1987 during a Polish archaeological expedition led by Professor Paul Waldenowiak. Carved from a single piece of mammoth ivory, it measured roughly 71 centimeters in length, weighed approximately 800 grams, and bore a curvature so precise that initial examiners questioned whether it could be functional. The shape was too clean, too deliberate, too engineered for something old enough to predate agriculture, pottery, and permanent settlement by tens of thousands of years. But engineering is exactly what the testing confirmed. A team of researchers built exact replicas from materials matched to the original's density and flex profile. In field throws and in wind tunnel simulations, the boomerang demonstrated gyroscopic precession, the same principle that keeps a spinning top upright, generated by its asymmetric airfoil cross-section. One surface was flat, the other was slightly convex. The leading edge was thinner than the trailing edge. These are not accidental features. They are design specifications, each one necessary for stable, returning flight. Remove any one of them and the object destabilizes in midair, tumbling instead of returning. The people who made this object lived during the last glacial maximum, when Central Europe was a treeless steppe gripped by mean annual temperatures between -4 and -6 degrees Celsius. They hunted reindeer, horse, and Arctic fox. They moved frequently, carried everything they owned, and left almost nothing behind that wasn't made of stone or bone, which means the boomerang was not a toy. It was a survival tool, possibly for hunting waterfowl over river corridors, possibly for driving small game toward waiting hunters, possibly for purposes that left no archaeological signature at all. The energy required to carve mammoth ivory into a calibrated airfoil is not trivial. It demands hours of grinding, shaping, testing, and refining. The investment calculus alone tells you something about how these people operated. No one invests that in a novelty. What makes the Blaswa find difficult to categorize is its isolation. No second boomerang has been recovered from the same layer. No workshop debris, no failed attempts, no half-carved blanks. Either the technology was so well understood that production waste was minimal, or the knowledge was carried from place to place by people who deliberately left no permanent record of the craft behind them. The single artifact sits in a museum in Krakow now, under glass, its surfaces still bearing the polish of the original maker's hands. The aerodynamic data, however, sits in a different kind of archive, one that raises a question nobody has answered convincingly. The testing was repeated. The results held. How did a community living on a frozen steppe, with no written language, no mathematics, no theory of fluid dynamics, arrive at an airfoil design that modern engineers would not validate for another 23,000 years? Number 9. The slit drum, Sub-Saharan Africa. Slit drums allowed prehistoric communities to transmit coded messages across distances exceeding 10 kilometers, making them the earliest known long-distance communication technology, predating written language by tens of thousands of years. If you're not subscribed yet, now's the time. This list only gets heavier from here. The slit drum's voice carried through equatorial forest where visibility dropped to under 20 meters, reaching settlements that no signal fire could touch and no runner could reach before nightfall. The tone, a deep, resonant pulse generated by striking the hollowed body of a log with a rubbery mallet, cut through canopy density that absorbed higher frequencies entirely. One drum, one player, a single signal that could reach an entire river basin. In the dense rainforests of Central and West Africa, where line-of-sight communication was impossible across even short distances. This instrument functioned as a relay network. The mechanism is deceptively simple. A length of hardwood, often hollowed by controlled burning and scraping, is carved with a long slit along one face, leaving two lips of unequal thickness. When struck, each lip produces a different pitch. The gap between those pitches and the rhythmic pattern in which they are struck forms a code. That code maps onto the tonal structure of the local language. In many Central African languages, meaning is carried by pitch as much as by consonant and vowel. The slit drum exploits this directly. A high-low-high pattern does not represent a word abstractly. It reproduces the tonal contour of the word itself. The drum speaks the language, or at least a compressed, high-information version of it. Ethnographic studies conducted across the Congo Basin in the 20th century documented message transmission chains that spanned over 10 kilometers. A drummer in one village sends a message. A listener in the next village within earshot repeats it on their own drum. Within minutes, information, a death, a warning, a call to gather crosses distances that would take a runner hours. The speed was the system's real achievement. European colonists recorded being startled by the speed of these networks. A message could outpace a man on horseback, and the system required no infrastructure beyond the drums themselves and the shared knowledge of the tonal code. The age of the technology is difficult to pin down, because wood does not preserve well in tropical archaeological contexts. The oldest surviving slit drums in museum collections date back only a few centuries, but the practice is almost certainly far older. Linguistic analysis suggests that tonal languages, the kind that make drum coding possible, predate the divergence of major African language families by tens of thousands of years. If the coding system requires a tonal language and tonal languages are ancient, then the communication system may be ancient too. The drum is a proxy for something older, a prehistoric understanding that sound could be structured, modulated, and decoded at a distance. That information could travel without a carrier. No written record marks the invention. No single inventor is named. The knowledge passed from generation to generation through practice alone, embedded in language itself. Some of those relay networks are still active in remote regions of Central Africa today, operating on the same principle they have for millennia. What has never been fully documented is the total range of the system. How far a message could travel in a single night across a fully functioning network, and whether there was ever a limit the drummers themselves recognized and designed around. The question remains open. Coming in at number 8. The travois Eurasian steppe. Before the wheel was invented, prehistoric peoples built load-bearing drag frames capable of hauling over 40 kilograms across broken terrain, and the design persisted virtually unchanged for at least 15 millennia. A wooden frame shaped like an elongated triangle drags behind a single mover, its two long poles running forward to a harness point, its crossbar carrying the load. That is the entire system. No axle, no rotating parts, no complex joinery, just timber, cordage, and the physics of friction distributed across two contact points instead of one. On open ground, the travois leaves parallel drag marks in the soil, marks that archaeologists have identified in fossilized trackways dating back to the late Pleistocene. The travois solves a problem that existed long before the wheel became viable: how to move more weight than a human can carry without breaking the carrier. The design distributes load across the full length of the poles, keeping the center of mass low and stable. On soft ground, steppe grass, snow, sand, the broad contact surface of the poles actually reduces sinking, functioning as a primitive form of weight displacement. A person who could carry 25 kilograms on their back could pull 40 or more on a travois. Because the load transfers from the spine to the hips and legs, and the ground absorbs much of the downward force through the dragging poles. Ethnographic parallels are extensive. Indigenous peoples of the North American Great Plains used dog-drawn travois well into the 19th century, and the designs observed by European settlers matched the basic configuration seen in much older Eurasian archaeological contexts. The continuity is striking. 15,000 years of continuity is not stagnation. It is convergence, a design that reached its optimum on the first attempt. A frame recovered or inferred from a 15,000-year-old site in the Eurasian steppe region would be functionally indistinguishable from one used by a Blackfoot family in Montana in the 1830s. The technology had no need to evolve because the problem it solved, moving weight across terrain without a road, had not changed. What is often missed is the implication for prehistoric mobility patterns. A community with travois capability is not tied to waterways for transport. It is not limited to what each individual can carry. It can move camp, relocate seasonal settlements, and carry raw materials, toolstone, hides, dried meat, over distances that would be impractical on foot alone. The travois effectively extends the operational range of a hunter-gatherer group by an order of magnitude. It also makes possible the accumulation and transport of material culture, items that are not strictly necessary for survival, but are kept because they can be kept. In this way, the travois may be one of the earliest technologies that allowed prehistoric peoples to possess more than they could carry, a threshold that changes the social structure of any group that crosses it. The archaeological record is sparse. Wood degrades, cordage rots. The evidence is mostly indirect, drag marks in sediment, where patterns on animal bones consistent with harness use, and the sudden appearance in the archaeological record of materials sourced from hundreds of kilometers away, suggesting transport capacity that foot carrying alone cannot explain. No wheel has ever been found predating roughly 3500 BCE. The travois operated for at least 11,000 years before anyone needed one. The travois itself has vanished, but the signature of what it enabled, distance, volume, weight, is still legible in the distribution of artifacts across the prehistoric landscape. Down to number 7. The loom weights of the Neolithic. Clay weights recovered from Neolithic settlements reveal that weavers were producing uniform, calibrated textiles, evidence of standardized manufacturing thousands of years before the Bronze Age. The weights were found in clusters, arranged in rows along the earthen floors of dwellings that had been sealed by fire and abandonment around 70 centuries ago. Each weight is a small, fired clay object roughly conical or cylindrical, pierced through the center by a single hole. Individually, they look unremarkable. In aggregate, they tell a different story. When archaeologists measured them, the weights within each cluster fell within a narrow mass range, typically varying by no more than 5 to 8%. That is not random. That is calibration. The precision was deliberate. Loom weights function as tension regulators on warp-weighted looms, among the oldest textile production devices ever identified. The vertical threads of a woven fabric, the warp, are suspended from a horizontal beam and pulled taut by weights tied to their lower ends. If the tension is uneven, the fabric produced is irregular, loose in some bands, tight in others, structurally compromised across the whole. Consistent weight means consistent tension. Consistent tension means consistent fabric. The warp-weighted loom is, in mechanical terms, a standing frame that turns gravitational force into tensile force. The weight does the work of a hand that would otherwise have to pull each thread tight individually. The clusters recovered from Saddle Huruk and other Neolithic sites across Anatolia and the eastern Mediterranean suggest that the people operating these looms understood this relationship explicitly and manufactured their weights to meet a specification. The production of a standardized weight is not a simple act. It requires selecting a consistent volume of clay, drying or firing it under controlled conditions, and verifying the result against a reference, either a template weight or a finished piece of fabric that serves as a quality benchmark. This is a process chain. It implies division of labor, quality control, and a shared understanding of acceptable tolerance. The tolerance levels observed, 5 to 8% variance, would be considered acceptable in many hand production contexts well into the medieval period. These are characteristics typically associated with much later periods: Bronze Age metal workshops, Roman engineering, early industrial manufacturing. Yet here they are, embedded in a settlement that predates the pyramids by 4,000 years. Textile fragments recovered from contemporary sites confirm that the output matched the precision of the tools. Under microscopic analysis, the weave densities of Neolithic fabrics show remarkably low variance within individual production groups. The thread counts cluster tightly. The spacing between warp and weft is regular. The consistency is too tight to be accidental. Someone, or some group of someone's, was producing cloth to a standard, not merely making cloth, but manufacturing it. The difference between making cloth and manufacturing cloth is the difference between a single meal and a food supply. One sustains a moment. The other sustains a system. What remains unresolved is the social mechanism behind the standardization. Were the weights produced by individual households following a shared convention, or were they made centrally and distributed? Was the standard enforced by trade expectations, a buyer rejecting fabric that didn't meet a known specification, or by the producer's own internal metrics? The weights themselves cannot answer these questions. They sit in museum storage drawers, cataloged and measured, each one a small piece of fired clay that testifies to a system of production whose rules were understood so thoroughly that no one needed to write them down. Number 6. The pump drill, a device that converted reciprocal hand motion into continuous rotational force using nothing but a cord, a flywheel weight, and a spindle, the same mechanical principle behind every drill used today. The spindle spins at over 2,000 revolutions per minute. The cord wrapped around it winds tight, then reverses, then winds again, each cycle driven by nothing more than a downward press of the operator's palm on a crossbar. The flywheel weight at the base stores angular momentum through each reversal, keeping the bit engaged with the material below it. Fire drills, bow drills, and hand drills all predate it, but none achieve continuous rotational motion. The pump drill does. And it does so with a mechanical elegance that engineers still reference when teaching the fundamentals of energy storage and conversion. The components are minimal: a straight wooden spindle, usually between 30 and 50 centimeters in length, a circular flywheel, typically a stone with a central perforation or a disc of fired clay mounted near the lower end, a crossbar drilled through its center to slide freely up and down the spindle, a length of cord tied at each end to the extremities of the crossbar and wrapped once or twice around the spindle shaft. That is the complete inventory. No metal, no fasteners, no adhesives. The entire device can be assembled from materials gathered in a single afternoon and disassembled for transport in seconds. The operation works as follows. The operator pushes the crossbar down. The cord wrapped around the spindle converts that linear downward force into rotational torque. The spindle spins. As it spins, the cord unwinds. When the crossbar reaches the bottom of its travel, the cord has fully unwound, and the flywheel's stored momentum keeps the spindle rotating just long enough to rewind the cord in reverse. The operator then releases pressure, and the rewound cord pulls the crossbar back upward, ready for the next downstroke. Each cycle adds rotational energy to the system. Within 3 or 4 strokes, the spindle is spinning continuously, alternating direction with each half cycle, but never stopping. The archaeological evidence is indirect but convergent. Perforated stone and clay discs, consistent in mass and diameter with flywheel weights, have been recovered from sites across Eurasia, Africa, and the Americas, with dates ranging from roughly 10,000 to 5,000 years ago. Many of these objects were previously cataloged as decorative pendants or spindle whorls for textile production, but their mass distribution, their wear patterns, and their association with drilled bead and bone artifacts tell a different story. A spindle whorl for textile work is light, designed to maintain slow, steady rotation. A pump drill flywheel is heavier, balanced for rapid momentum storage and release. The distinction is functional, and it matters. What the pump drill represents is a conceptual leap that is easy to overlook because the device is so simple. Every drill that exists today, every power drill, every lathe, every CNC spindle operates on the same fundamental principle: rotational force applied to a cutting or boring surface. The pump drill is the earliest known device that generates and sustains that rotational force through a mechanical feedback loop. The operator does not spin the bit directly. The operator energizes a system, and the system spins the bit. That abstraction, the separation of input force from output motion, is the foundation of every machine that followed. The pump drill is not a tool, it is a machine. The dating remains uncertain because the organic components, the cord, the crossbar, often the spindle itself, degrade without trace. What survives are the weights, and the weights, with their calibrated mass and their scented perforations, are still being found in contexts that push the timeline further back with each decade of fieldwork. The true origin of the device may never be pinned to a single site or century. The weights keep appearing. The physics haven't changed. Number 5. Fish weirs and tidal traps. Stone and timber structures built across estuarine channels demonstrate that prehistoric communities engineered tidal harvesting systems calibrated to lunar cycles, some still visible from satellite imagery. The water drops, the fish remain. That is the entire principle, and it is devastatingly effective. A weir, a low wall of stone, timber, or woven brush, is built across a tidal channel or estuarine inlet at a height that sits just below the high tide waterline. As the tide rises, water flows over the wall, carrying fish and other marine life into the enclosure behind it. When the tide falls, the water drains back through gaps or over the top, but the fish, now trapped behind the barrier, cannot find the exit. The harvester returns at low tide and collects what the ocean delivered. No nets, no boats, no pursuit, just a wall, a tide cycle, and patience. The remains of these structures have been identified along coastlines from Scandinavia to Chile, with dates clustering between roughly 6,000 and 4,000 years before the present. In some locations, the Severn estuary in Britain, the coast of Brittany in France, the bays of southern Chile, the stone foundations are still intact enough to be mapped from aerial photography. Satellite imagery has revealed weir networks extending across kilometers of tidal flat, their outlines sharpened by the contrast between the stone walls and the surrounding sediment. These are not accidental accumulations of rock. They are planned constructions, oriented perpendicular to tidal flow, with funnel-shaped entry points that exploit the hydrodynamics of moving water. The engineering is more sophisticated than it appears. A weir that is too tall blocks fish from entering on the flood tide. A weir that is too low fails to retain them on the ebb. The wall height must be calibrated to the tidal amplitude, the difference between high and low water, at the specific location where it is built. Tidal amplitude varies not only by region but by season, by lunar phase, and by local topography. A weir built for a spring tide, the highest tide, which occurs near the full and new moon, will overtop on a neap tide and underperform on a mean tide. Some of the weir systems excavated in Europe show evidence of modular construction. Sections that could be added or removed to adjust the effective height of the barrier in response to seasonal tidal variation. That adjustment implies observation, record-keeping, and predictive modeling, not of tides in the abstract, but of the specific tidal behavior at a specific stretch of coastline over months and years. The scale of harvest these systems enabled is difficult to overstate. A single well-placed weir on a productive estuary can trap hundreds of kilograms of fish per tidal cycle. Archaeological deposits near weir sites in Scandinavia and Scotland contain fish bone assemblages in the hundreds of thousands, dominated by species that migrate inshore on flood tides: herring, eel, flatfish, smelt. The volume suggests not subsistence harvesting but surplus production. The fish were processed, dried, smoked, salted, and stored or traded. A weir is not a fishing tool. It is a food infrastructure asset built to operate continuously with minimal labor input once constructed. Some of the weir sites show evidence of repeated rebuilding over centuries. The structures were maintained, modified, and expanded across generations, suggesting continuity of knowledge, ownership, or at least persistent use rights over the locations where they stood. The people who built them understood that the sea could be shaped, not just harvested. The tides still rise and fall on those same coastlines today. In a few places, the water still drops and the stones still hold. Number 4. The microlithic composite weapon, Europe and Africa. Stone Age hunters designed modular weapons with interchangeable microblades that could be snapped in and out of shafts. A standardized, interchangeable parts system at least 40,000 years before the concept was formally described. A hunter pulls a broken microblade from the groove of a wooden shaft, drops it into a pouch, and presses a replacement into the same slot, secured with a strip of birch tar that sets in under a minute. The weapon is ready again. Total downtime, seconds. No resharpening, no recarving, no return to camp. The microblade, a small, geometrically precise flint segment, often no larger than a fingernail, is the cartridge of prehistoric weaponry. and the system that uses it is the earliest known example of interchangeable, modular components in human toolmaking. Microliths first appear in the archaeological record in southern and eastern Africa roughly 45 to 50,000 years ago, and spread across Eurasia over the next 30 millennia. They are not tools in themselves. They are components designed to be set into rows along the edges or tips of spear shafts, arrow shafts, or cutting implements, held in place by adhesives and binding. A single weapon might carry 6, 10, or 20 microliths, each one producing a cutting edge, a piercing point, or a barbed surface. When one breaks on impact, it is removed and replaced. The shaft survives. The adhesive is reapplied. The weapon returns to service. The standardization is what sets microlithic technology apart from earlier stone tool traditions. Acheulean hand axes were individual pieces, each one napped to a general shape, each one unique. Levallois flakes were more consistent but still produced as whole tools. Microliths are different. They are produced in batches to a template with remarkably low variance in shape, thickness, and edge angle. The geometric forms, triangles, trapezoids, crescents, rectangles, appear consistently across sites separated by thousands of kilometers and thousands of years. This is not independent reinvention. This is a shared technical standard, a specification, maintained across cultures, continents, and millennia. The production process itself reveals a high degree of planning. A core is prepared with a specific platform geometry. A series of blades is struck from that core, each one roughly the same size and shape. Those blades are then snapped or trimmed into the final microlith form, often using a notching technique that produces a clean, predictable fracture. The napper is not making one tool at a time. The napper is running a production line, turning a single core into a batch of interchangeable parts, each one designed to fit any weapon in the inventory. The tactical advantage is enormous. A hunter carrying a hafted weapon with replaceable microliths enters the field with a repair kit in a pouch. A broken edge is not a broken weapon. It is a maintenance event, brief, routine, survivable. This changes the calculus of the hunt. A group armed with composite weapons can sustain longer pursuits, engage larger or more dangerous prey, and absorb more damage to their equipment without losing operational capability. The modular system also allows rapid reconfiguration. The same shaft can be fitted with piercing points for large game, barbed edges for fishing, or serrated rows for butchery. One platform, multiple loadouts. The concept of interchangeable parts is conventionally attributed to Eli Whitney and the early industrial manufacturers of the late 18th century. The microlithic record pushes that origin back by at least 40 millennia. The people who designed this system never wrote down the specification. They didn't need to. The standard was embedded in the production process itself, in the angle of the core, the force of the strike, the shape of the snap. The knowledge lived in the hands. Number 3. Bark tanning vats, Northern Europe. Excavated pits lined with oak bark residue show that prehistoric tanners ran multi-week chemical processes to transform raw hide into stable leather, essentially operating batch processing factories before metal tools existed. The hide came off the animal stiff, wet, and perishable. Without treatment, it would begin to putrefy within hours. Within days, it would rot. Within weeks, it would be gone, consumed by bacteria, broken down by enzymes, returned to the soil from which the animal had come. The people who dug these pits knew that. They also knew that submerging that same hide in a solution of crushed oak bark and water would halt the decay and transform the material into something entirely different. Leather, flexible, durable, resistant to water, resistant to rot, stable for years, sometimes decades. The process takes weeks. It cannot be rushed, and it was being run in purpose-built pits roughly 7,000 years ago. The vats were discovered in waterlogged sites across northern Europe, in Denmark, in the Netherlands, in the British Isles, where the anaerobic conditions of peat and mud preserved the organic residues that would have vanished in any dry environment. The pits are rectangular or oval, typically 1 to 2 meters in length, lined with timber or wattle, and filled with layers of oak bark fragments. Chemical analysis of the fill material confirmed the presence of tannins, the astringent polyphenolic compounds that bind to collagen fibers in raw hide, cross-linking them and rendering them resistant to microbial attack. The tannins are the active agent. The oak bark is the source. The pit is the reactor. Tanning is not a simple dip and soak operation. It is a multi-stage chemical process that demands precise control. The hide must first be dehaired, typically by soaking in a mild alkaline solution, often made from wood ash and water. It must then be cleaned, fleshed, and thinned to a uniform thickness. Only then is it ready for the tanning bath, where it must remain immersed for a minimum of 2 to 4 weeks, depending on the thickness of the hide and the concentration of the tannin solution. During that time, the tannins penetrate the collagen matrix gradually, from the surface inward. If the concentration is too high, the outer layers harden while the interior remains raw. If too low, the process stalls and the hide begins to degrade before tanning is complete. The tanner must monitor, adjust, and wait. The presence of multiple pits at several sites suggests batch processing different hides at different stages of the cycle, all running in parallel. This is not a household activity. This is a production operation, with throughput, scheduling, and yield considerations. The scale implies surplus, more leather being produced than the immediate community could consume, which means trade, which means value, which means someone was managing the inventory. All of this is occurring in a period before metal tools, before written records, before any formal economic system. The pits themselves are the documentation. What has not been fully reconstructed is the knowledge chain. How was the tanning property of oak bark first identified? Was it accidental, a hide left in a bark-lined pit that emerged transformed? Or was it the product of deliberate experimentation with plant materials? The ethnographic record shows that tanning agents were extracted from a wide range of sources across different cultures: chestnut, hemlock, sumac, acacia. Each one was discovered independently, each one processed differently, each one requiring its own timing and concentration. The knowledge is too specific, too non-obvious to have been discovered once and spread. It was discovered and rediscovered and refined over and over by people who had no way to write down what they were learning but who passed it on anyway. The vats are still there. Some still smell of oak. Number 2. Bone cauterization tools, Europe. Human remains dated to roughly 7,000 years ago show evidence of deliberate heat cauterization of wounds, suggesting prehistoric healers understood that controlled burning could prevent fatal infection long before germ theory. The skull lay in a Neolithic burial site in France, and across its parietal bone ran a groove, clean, linear, and bordered by a rim of charred and fused bone tissue. The pattern was not consistent with trauma, disease, or post-mortem damage. Under microscopy, the thermal discoloration penetrated the bone to a consistent depth, and the edges showed the kind of controlled, localized heat exposure that only comes from deliberate application. This was not a body caught in a fire. This was a wound that someone had intentionally burned. Cauterization, the application of heat to living tissue to seal bleeding, destroy damaged flesh, or prevent infection, is a documented medical practice in written records dating back to Hippocrates and the Egyptian surgical papyri. But the skeletal evidence from Neolithic Europe pushes the timeline back by millennia. Multiple sites across France, Germany, and the Iberian Peninsula have yielded remains showing healed bone lesions with thermal signatures consistent with cauterization. In several cases, the individuals survived the procedure. New bone growth around the cauterized area indicates that they lived for years afterward. The healing is the proof. A failed cauterization leaves a different signature: infection channels, necrotic cavities, incomplete closure. The healed cases show none of that. The procedure worked. The tools were likely heated stone blades, fire-hardened bone points, or metal-free implements capable of sustaining and transferring high temperatures to a small, precise contact area. None have been conclusively identified in direct association with the remains, but experimental archaeology has demonstrated that flint blades heated to between 300 and 400 degrees Celsius can produce cauterization marks identical to those observed on the ancient bones. The flint holds heat long enough to seal a wound edge without causing widespread tissue destruction. The operator needs a heat source, a tool, and the judgment to apply the right temperature for the right duration. That judgment is the critical variable. Too little heat fails to seal the wound and invites infection. Too much heat kills surrounding tissue and causes necrosis, which also invites infection. The window between effective cauterization and thermal injury is narrow, and it varies by tissue type, wound depth, and tool material. The people performing these procedures were operating without anatomy texts, without thermometers, without any theoretical framework for why burning a wound might prevent it from killing the patient. They had observation. They had repetition. They had the accumulated evidence of every previous attempt, successful and fatal, encoded in practice. The existence of cauterization in the Neolithic implies more than medical knowledge. It implies a social structure capable of supporting a healer, someone with enough specialized skill that the community valued their expertise enough to keep them from hunting, gathering, or building while they treated the injured. It implies a risk calculus, the willingness to inflict immediate pain and tissue damage in exchange for a probability of survival high enough to justify the attempt. And it implies memory, a way of transmitting the knowledge of temperature, timing, and technique from one practitioner to the next across generations. The bones do not record who held the blade. They record only that someone did and that the patient lived. What we do not know is how many times the procedure was attempted and failed, because the failures, the ones who died of infection or thermal shock, would not bear the healed bone that identifies the successes. The survival rate is invisible. Only the survivors remain. Number 1. The one you came for. Heat treatment of silkrit. Approximately 72,000 years ago, humans discovered that heating silkrit to around 350 degrees Celsius for sustained periods transformed it into a superior flacking material, the earliest known instance of deliberate materials engineering on Earth. The silkrit came out of the fire different from how it went in. Before heating, it was coarse, grainy, and unpredictable. When struck, it fractured along irregular planes, producing flakes with ragged edges and inconsistent shapes. After heating, it was something else entirely. The same stone, now treated, flaked cleanly and predictably, with a glassy conchoidal fracture that let a skilled napper produce long, thin, razor-sharp blades with minimal waste. The material had been changed at a structural level. Not shaped. Changed. And the people who changed it understood what they were doing well enough to repeat the process, refine it, and teach it to the next generation. The evidence comes from Pinnacle Point, a series of cave sites on the southern coast of South Africa, where teams led by Curtis Marion and Kyle Brown identified heat-treated silkrit tools in layers dated to approximately 72,000 years ago. The dating is robust, based on optically stimulated luminescence and uranium series dating of flowstones, and the material signatures are unambiguous. Under scanning electron microscopy, the heated silkrit shows a recrystallized silica matrix, quartz grains partially fused at their boundaries, filling the pores and microfractures that made the raw stone brittle and inconsistent. The heat had sintered the rock, essentially turning it into a naturally occurring glass-ceramic composite. The temperature window is narrow. Experimental replications have shown that the transformation occurs most effectively between approximately 300 and 350 degrees Celsius, sustained for periods ranging from several hours to a full day. Below 300 degrees, the structural change is incomplete. Above 400, the stone begins to fracture spontaneously, developing thermal stress cracks that render it useless for knapping. The prehistoric practitioners had to hold the material within a band of roughly 50 degrees, without thermometers, without dials, without any instrument beyond their own senses, long enough to complete the transformation. They did this by burying the stone beneath hearth fires, using the insulating properties of sand and ash to moderate the temperature and distribute the heat evenly across the raw material. This is not accidental heat exposure. Rocks that happen to lie near a fire do not undergo this transformation. The temperature is too variable, the exposure too brief, the result too inconsistent. The Pinnacle Point material shows uniform heat treatment across entire batches of silkrit, consistent with a controlled process. The nappers selected raw silkrit from specific geological sources, transported it to habitation sites, prepared hearths or pit furnaces, placed the stone within those features, managed the fire for hours, then removed and worked the treated material. The process chain involves planning, resource allocation, and a time investment that yields no return until the final stage, when the treated stone is struck and the blades are produced. The implications are difficult to overstate. Heat treatment of silkreed is not toolmaking. It is materials engineering. The practitioner is not modifying the shape of a raw material. They are modifying the material's physical properties. They are inducing a phase change in a mineral substrate through controlled thermal input, and they are doing so with a precision that suggests systematic experimentation, observation, and knowledge transmission over multiple generations. The earliest known example, 72,000 years ago, predates agriculture by roughly 60,000 years, metal smelting by 65,000, and the first documented chemical process by a margin so large it redefines the term. The knowledge did not stay at Pinnacle Point. Heat-treated silkreed appears at sites across southern Africa, spanning hundreds of kilometers and thousands of years, with consistent temperature signatures and production techniques. The practice spread, whether through migration, trade, or cultural transmission, and persisted until at least 50,000 years ago, when it begins to fade from the record for reasons that remain unclear. What is clear is that the people who developed this process operated at a cognitive level fully capable of abstraction, long-term planning, and systematic experimentation. The same capabilities that would later produce metallurgy, chemistry, and every engineered material that followed. The hearths at Pinnacle Point have gone cold. The silkreed they transformed still cuts.